Write down the meaning of the term reversible reaction. So a reversible reaction is a reaction where the products can be turned back into reactants. That is the answer to 6.1. 6.2, state Le Chatelier's principle. Okay, this is very key to chemical equilibrium. Chemical equilibrium is basically based on Le Chatelier's principle. Well, it says that when equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring a reaction that opposes the change. That is Le Chatelier's principle. Let's take a look at 6.3 and 6.3.1. A change was made to the equilibrium mixture at t is equals to 80 seconds. 6.3.1, write down the change made at t is equals to 80 seconds. So let's go ahead and have a look. This is t is equals to 80 seconds. We have a reaction to AB giving us and getting A2 plus B2, right? At t is equals to 80 seconds, you can see clearly that the concentration, not the concentration, but the number of moles. The number of moles of A2 are increased. There's an increase in the number of moles of A2. And then as a consequence, when the system wants to reinstate a new equilibrium, the reaction that reduces the number of A2 is going to be favored, which is the reverse reaction. That is why we see the number of moles of B2 decreasing and the number of moles of AB increasing. So the answer to 6.3.1, number of moles of A2 are increased, okay? So the number of moles of A2 increase. That is the change that is made at t is equals to 80. 6.3.2, use Le Chatelier's principle to explain how the system reacts to this change. Okay, I think I've touched on that, but let's just go through it again. So let's take a look at our reaction. If you increase the number of moles of A2, the system will want to reinstate a new equilibrium by favoring the reaction that reduces the number of moles of A2. Clearly, the reverse reaction reduces the number of moles of A2 because A2 plus B2 will be turned to AB. So that is how the system will react to this change. It will reinstate a new equilibrium by favoring the reverse reaction that leads to less number of moles of A2. 6.3.2. 6.4. Let's take a look at 6.4. So in 6.4, calculate the equilibrium constant Kc at t is equals to 120 seconds. And then the allocation is 4 marks, right? Yeah, this is a nice question, unlike the questions we usually have where you have 8 marks, 9 marks, so on and so on. So to find the Kc, we need to say that the concentration of the products, so we have A2 and B2, divided by the concentration of the reactants. We have AB. We have to take the concentration of AB to the power 2. We are doing that because of this balancing coefficient, okay? So Kc will be equals to, we're interested in T is equals to 120. T is equals to 120. We have the number of moles of AB, the number of moles of A, and the number of moles of B2. And we are given the volume in our question statement. It is said to be 4 decimeter cube. Okay, so let's go ahead and find the number of moles, not the number of moles, but the concentration of A2. How many number of moles do we have? We have 8 number of moles for A2. We have 8 moles, right? So we're going to have 8 divided by 4. Number of moles divided by volume will give you the concentration. Multiplied by the concentration of B2. How many moles do we have? We have 2 moles. So that is going to be 2 divided by 4. Everything divided by the concentration of AB. We have 10 moles of AB when the temperature is 120 degrees. So that's going to be 10 divided by 4 to the power 2 because of the balancing coefficients. So now it's just a matter of putting that in my calculator. So let me go ahead and do that fairly quick. Divided by 10 divided by 4, everything to the power 2. I have 0.16. So there we go. That is our Kc at t is equals to 120 seconds. Okay, 6.5. At t is equals to 130 seconds, the temperature of the system is decreased to 100 degrees Celsius. Okay, and then 6.5.1, let's draw a potential energy diagram for this reaction. Okay, let's make sense of the situation we have. Let's go to our graph and look at T is equals to 130 degrees because that is where the temperature is decreased, and see how our reaction is reacting to that change. We have 2AB to give and to get A2 plus B2. Let's go to T is equals to 130 degrees. Let me just erase all this for the sake of clarity and draw a line at T is equals to 130 degrees. Okay, at T is equals to 130 degrees, let's take a look at the amount of AB. The amount of AB increases, the amount of A2 decreases. Same is true with regards to the amount of B2. So our reactants, the amount of reactants we have decreases while the amount of products increases. Okay, so let's make sense of that. Temperature was decreased and the reverse reaction was favored. If the number of moles of A2 and B2 are decreasing, it means that that reaction was favored. A2 and B2 were converted to AB. So decrease in temperature, let's make sense of that. So when the temperature was decreased, reverse reaction was favored. Which reaction is favored by decrease in temperature? That is exothermic. So the reverse reaction is exothermic because it was favored by decrease in temperature, which tells us that the forward reaction is endothermic. Okay, right. So now we need to draw a potential energy diagram for a endothermic reaction, for a reaction where the forward reaction is endothermic. So what are we going to have? Let me show you. We have our y-axis and we have our x-axis. So cost of reaction and potential energy in kilojoules per mole, usually. Okay, so if we're saying that forward is endothermic, then we're gonna have something that looks like this. We have our products A2 plus B2. We have our reactant AB. Okay, I think that is all we need. We can obviously show that this is our activated complex. Let me show clearly that the energy of the products is greater than that of the reactants. Let me show that, okay? So that when I show my enthalpy, it's easy to see, right? So this is my enthalpy. Energy of products minus energy of reactants. 6.5.2, will the equilibrium constant Kc at 100 degrees Celsius be greater than, less than, or equal to the Kc at 150 degrees Celsius? Explain the answer. Okay, it will be less than. It will be less than. Okay, let's explain why it will be less than. It will be less than because when the temperature is decreased at 100 degrees Celsius, we're going to have less product compared to at 150. Because if you increase the temperature from 100 to 150, your forward reaction is going to be favored. You're going to have more products versus the reactants. So 6.5.2, we have less than. And the reason I just gave you right now. Forward reaction is endothermic. So if you decrease the temperature, reverse reaction is going to be favored. We have less product, so the value of Kc goes down. Okay, because Kc is products divided by reactants. That is why we are seeing less than. 6.6. Let's take a look at this one. The initial reaction now takes place in the presence of a catalyst at 150 degrees Celsius. Describe the changes that will be observed on the graph between t is equals to 0 and t is equals to 60. So let me know in the comments, how did you answer 6.6? What I'm currently thinking is that if we add a catalyst, then we will provide an alternative path of lower activation energy. So both the forward and the reverse are going to be favored, right? The rate of reaction is going to be increased. So we are gonna reach equilibrium quicker, right? Before t is equals to 40, if we are reaching equilibrium at t is equals to 40. I wonder how you phrased 6.6. So just leave a comment and let me know how you answer the question. When the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that opposes the disturbance. That is 6.1 Chartelia's principle, and we're going to use that to answer 6.2. Hydrogen gas is prepared by the reaction of methane and steam, as shown in the following balance equation. We can clearly see that we have methane, H2O, to form the hydrogen gas and carbon monoxide. Okay, and then the question is saying 6.2.1, how will the following changes affect the yield of hydrogen gas? Adding more methane. So in our reaction, you can clearly see that CH4 is one of the reactants. So if you increase the amount of CH4, the forward reaction will be favored so that CH4 is used up. The system reinstates a new equilibrium by favoring the reaction that opposes the change. So 6.2.1, adding more CH4, more methane, would increase the yield of H2. So it increases the yield of hydrogen gas. It increases the yield of hydrogen gas. Why is that so? Per Chartelia's principle, when there's a disturbance in a closed system, the system reinstates a new equilibrium by favoring the reaction that opposes the change. We have the amount of CH4 increasing. So the system will favor the forward reaction so that CH4 can be used up. And as a consequence of that, the amount of hydrogen gas produced would increase. And then 6.2.2, a decrease in the volume of the container. So this is what we need to understand. A decrease in the volume means an increase in the pressure. Right. So there's an increase in the pressure in our system. How will the system reinstate the new equilibrium? It wants to decrease this pressure. And how does it achieve that? How does the system decrease pressure? It favors the reaction that leads to less number of moles of gas. Okay, but if you take a look at our reaction, we can see that we have methane as a gas, H2O as a gas, carbon monoxide as a gas, and hydrogen gas as a gas. So we need to take a look at the left hand side and at the right hand side, the products and the reactants. In the products, we have 4 moles of gas, right? 3 from hydrogen gas and 1 from carbon monoxide. And then on the reactants, we have 2 moles of gas, right? 1 from methane and 1 from H2O. So it means that if the volume has been decreased and the pressure has went up and we want to decrease the number of moles of gas, then we need to favor reverse reaction. We need to favor reverse reaction because the reactants have less number of moles of gas compared to the products. So in this case, the yield of hydrogen gas would decrease. So we have decrease in the yield of hydrogen gas. And why is that so? For the reasons I just gave, right? We are decreasing the volume, the pressure increases. The system wants to reinstate the equilibrium by favoring a reaction that opposes the change. Since we have increased the pressure, the system wants to decrease the pressure. So reverse reaction will be favored because it leads to less number of moles of gas, hence less pressure. So that is 6.2.2 right there. Okay, let's take a look at 6.3. The sketch graph below shows the changes in the number of moles of methane, steam, and carbon monoxide as the reaction proceeds for the preparation of hydrogen gas in a 2 decimeter cube container. Okay, 6.3, write down the reason why there is no change in the number of moles of each of the gases between T1 and T2. Okay, we can see that the number of moles of all those gases between T1 and T2 remains the same. There is no change. Why is that? That is what we need to explain.
the reaction has reached chemical equilibrium. The rate of forward reaction is equals to the rate of reverse reaction. So here we just reached chemical equilibrium. That is why we see no change in the number of moles of the gases. Okay, 6.3. Let's take a look at 6.4. 6.4 says, use the information on the graph and calculate the equilibrium constant Kc for this reaction at temperature T. Okay, there we go. So that table, I think that table takes away from chemistry, because most people can sketch that table, the fill in some values, but they don't really understand what is going on. You can actually answer these questions in the absence of tables, right? But most people use a table. So let's just go ahead and do that also. What do we start with? Okay, let's have our methane gas, CH4, and then H2O, carbon monoxide, and then the balancing coefficient of hydrogen gas is 3. And then this is the initial number of moles. This is the change, number of moles at equilibrium, and the concentration. So let's take a look at our graph. We can see that initially at T is equals to 0, we start with 1.4 number of moles of methane. So this is 1.4. And then that of H2O is 1.2. So we have 1.2. Carbon monoxide starts at 0, same as hydrogen gas. Okay. And then take a look at this at T2 or T1. When we have reached our equilibrium, we find that the number of moles of carbon monoxide is 0.6. The number of moles of carbon monoxide at equilibrium. So we have 0.6. So clearly, the forward reaction was favored, right? We have more products than we had initially. So it means that here there was an increase of 0.6, right? Meaning that for H2O, there was a decrease of 0.6 as the balancing coefficient is 1:1. If the balancing coefficient was, let's say, maybe 2:1, and then carbon monoxide is 1 and H2O is 2, then we would have minus 0.6 multiplied by 2. But here it is just 1. And then minus 0.6 also, because it goes down. And here we have plus 0.6 multiplied by 3. 0.6 multiplied by 3. Right, we are multiplying by 3 because of the balancing coefficient. Right, so this is 1.8. So 1.4 minus 0.6, that is 0.8. And then 1.2 minus 0.6, that is 0.6. And then 0 plus 0.6, 0.6. 0 plus 1.8, that is 1.8. So we have the number of moles at equilibrium. We need to find the concentration by dividing with 2 decimeter cube the volume of the container. If we do that, 0.8 divided by 2, 0.4. 0.6 divided by 2, 0.3. 0.6 divided by 2, once more, 0.3. 1.8 divided by 2, that is 0.9. We have the concentrations at equilibrium. We can go ahead and find Kc by saying that Kc is equals to the products divided by the reactants. Carbon monoxide, hydrogen gas to the power 3. The power is coming from the balancing coefficient. And then CH4 multiplied by the concentration of H2O. So there we go. The concentration of carbon monoxide is 0.3. That of hydrogen gas is 0.9. And we take that to the power 3. Everything divided by methane. 0.4 multiplied by water, which is 0.3. So we put that in our calculators. Let me just do that real quick. 0.3 multiplied by 0.9 to the power 3 divided by 0.4 multiplied by 0.3. And then I get 1.82. So 1.82. Right, that's it. We don't have an ISI unit for Kc. So there we go. That is the Kc. That is the equilibrium constant for this reaction. That is 6.4. So tell me, here's a question for you. 6.5. The temperature T is decreased. The temperature T is decreased. How will this change affect the Kc value for the above reaction? Right, only increase, decrease, or remain the same. The temperature T is decreased. How will this change affect the Kc value? Let me know in the comments what you think the answer to this question is and why. Here we go.
We have a reaction between carbon and sulfur. The system reaches equilibrium at temperature T in a sealed 2 decimeter container. The Kc value is 9.4 at a temperature T. The first question, 6.1, we're supposed to state Le Chatelier's principle. It says that when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that opposes the disturbance. That is Le Chatelier's principle. 6.1. 6.2, on the other hand, at equilibrium, 1 mole of CS2 is present in the container. Calculate the concentration of S present at equilibrium. What is the information we have? We have the Kc is equals to 9.4. We have the number of moles of CS2 at equilibrium. So the number of moles is 1 mole. But we are given the volume, it is said to be 2 decimeter cube. So we can find the concentration of CS2 at equilibrium. So the concentration of CS2 will be equals to the number of moles divided by the volume. This is going to be 1 divided by 2, which is 0.5 moles per decimeter cube. So we have the Kc and we have the concentration of CS2 at equilibrium. How can we possibly find the concentration of S at equilibrium? We can simply say that Kc is equals to the concentration of the products. So that is the concentration of CS2 divided by the concentration of the reactants. On the reaction side, we have carbon and sulfur, but carbon is a solid, so we don't include it in our Kc expression. In the denominator, we are only going to have sulfur to the power 2. Where is the power of 2 coming from? The balancing coefficient. If we go ahead and substitute, we're going to get 9.4 being equals to the concentration of CS2, 0.5 divided by the concentration of S, sulfur squared. So the concentration of sulfur will be equals to 0.5 divided by 9.4. Everything to the power 1 divided by 2. We're taking square roots on both sides. If you put that in your calculator, you're going to get 0.23 moles per decimeter cube as the concentration of sulfur. There we go, 6.2. Let's go ahead and take a look at 6.3. So in 6.3, the volume of the container is now doubled. After a while, a new equilibrium is established. 6.3. How will the amount of sulfur change as this new equilibrium is established? Choose from increase, decrease, or remain the same. Okay, let's take a look at our equation. We have carbon plus 2 atoms of sulfur to give us CS2. Well, our reaction is reversible. What is happening? We are increasing the volume, right? So let's just note that we increase the volume. According to Le Chatelier's principle, if you increase the volume, the system will try to decrease the volume by favoring the reaction that opposes the change. The volume is increased. Increasing the volume decreases the concentration. This decreases the concentration. How can the system react to this change by increasing the concentration? It is going to favor the reaction that leads to more number of moles so that the concentration can increase again. Let's take a look at our reaction. On the right hand side, we have a balancing coefficient of 1 on our gas. And then on the left hand side, on the gas, we have a balancing coefficient of 2. If reverse reaction is favored, that is going to lead to more number of moles, as we have a balancing coefficient of 2 versus 1. So here, the reverse reaction is favored when the volume is doubled. When the reverse reaction is favored, then the amount of sulfur is going to increase. So the answer to 6.3 is increases. We don't have to answer 6.4 because in answering 6.3, we actually addressed it. Let's take a look at 6.5. If the concentration of CS2 changes by x mole per decimeter cube, write down an expression for the equilibrium constant Kc in terms of x. Show all your workings. No simplification or solving for x is required. Let's go ahead and take a look. The Kc is not going to change because in order to change the Kc value, we need to change the temperature, right? So the Kc is still equals to 9.4. The only change that is occurring is with regards to the concentration. Well, let's go ahead and draw our table. There we go. Before we doubled the volume, the concentration of sulfur was 0.23 and the concentration of CS2 was 0.5. When you double the volume, the concentration of sulfur is now going to be equals to 0.23 divided by 2, which is equals to 0.115. On the other hand, the concentration of CS2, 0.5 divided by 2, which will give us 0.25. This is because the volume is being doubled, so the concentration is being halved. So the initial concentration of sulfur, we have 0.115, while the initial concentration of CS2, we have 0.25. We are told that the concentration of CS2 changes by x. In 6.3 and 6.4, we've already explained that the reverse reaction is going to be favored. So this is going to be minus x. The concentration of CS2 is going to decrease by x. While on the other hand, the concentration of CS2 is going to increase by plus 2x. Why plus 2x? The balancing coefficient of sulfur is 2. So that's why we have that there. When I have 0.25 minus x, 0.115 plus 2x. We're going to have Kc being equals to the concentration of CS2 divided by the concentration of sulfur squared. So 9.4 is equals to 0.25 minus x divided by 0.115 plus x squared. This is our Kc expression.
Define the term chemical equilibrium. I'm actually not reading the question, but telling you to define the term chemical equilibrium. That is 6.1.1. Let's take a look at 6.1.2. At T1, oxygen, O2, was added to the container. Write down the letter that represents O2. Choose from X, Y, or Z. Let's go through the question statement and see what is happening. So the reaction of carbon monoxide gas CO with oxygen gas O2 is investigated. The reaction reaches equilibrium in a closed container at constant temperature T degrees Celsius, according to the balance equation below, as we can clearly see here given to us. Changes to the conditions of equilibrium are made at different times. The graph shows the results obtained, X, Y, and Z. That represents the gases in the above reaction. Back to our equation. At T1, oxygen O2 was added to the container, rather than the letter that represents O2. So when we look at our reaction here, X, Y, Z, it should be easy to see that Z is what is added at T1, right? So that answers our question 6.1.2. We're supposed to write down the letter that represents O2 from X, Y, or Z. So
the answer to 6.1.2, we have X. That is the letter that represents O2. Yeah, clearly there is a spike with regards to X at T1. Yeah, so clearly it is oxygen, because that was what is added at T1, we are told. We're not supposed to give a reason, but I've sort of told you why that is. 6.1.3. At T2, the pressure is adjusted by changing the volume of the container. Was the pressure increased or decreased? How many marks? 1. Okay, I wish it was 2 or 3, because we really have to think. Well, 6.1.46 we must explain, so I guess the 1 mark is justified. So let's take a look at T2. At T2, X goes down, right? So O2 goes down at T2. And then we have one other substance, Y, that goes down, and Z that goes up. Okay, so we are told that the change that was made is with regards to pressure, right? So let's take a look at our reaction. On the right hand side, we have 2 plus, let me use something lighter. We have 2, okay, that is even worse. What is happening? We have 2 plus 1 moles of oxygen on the right hand side, right? We have 3 moles of oxygen on the right hand side, and then on the left hand side we have 2. Okay, why are we doing this? We want to sort of see how our reaction will react, how our system will react to a disturbance, because the system wants to oppose the disturbance, right? So what happened to O2? O2 at T2, it went down. Okay, so we're saying that the concentration of O2 goes down, okay? And then look at Y. Y also goes down. But after Y goes down, it doesn't bounce right up, because if you take a look at O2, O2 bounces up after it goes down. And then Y goes down, but keeps on going down. And then Z goes down, but bounces up together with O2, right? So because the change is with regards to pressure, we can say that O2, it's X, and Z is actually carbon monoxide. Z has to be carbon monoxide. So this is CO. And then Y should be carbon dioxide, CO2. So, okay, O2 did go down, but ultimately it went up. So let's change that. O2 actually goes up ultimately, because when the pressure is changed, right, they all go down. Now we can conclude and say that the pressure was decreased here. How do we know that the pressure was decreased? The pressure was decreased because the rate of reaction, the concentration of all the reactants went down momentarily, as we can clearly see here. So O2 goes down for a moment, and then it goes up. Carbon monoxide goes down for a moment, and then it goes up, as we can clearly see in the diagram that we're given, right? But CO2 goes down and stays there. It goes down and stays there. So the pressure was decreased here, right? And then as the pressure was decreased, reverse reaction was favored. Reverse reaction was favored. Reverse reaction is favored because it is the one that leads to more number of moles of gas, hence increasing the pressure. So what is our question again? Was the pressure increased or decreased? The pressure was decreased. The pressure was decreased. 6.1.4. Why are we saying that the pressure was decreased? Reverse reaction was favored. Well, I'm not going to write. Let me just tell you. Reverse reaction was favored. And then reverse reaction, when it is favored, it leads to more number of moles of gas, hence increasing the pressure. The only way our system would react in this manner, where it leads to more number of moles of gas where the pressure is increased, is if there was a decrease in the pressure.
right? So that is the answer to 6.1.3 and 6.1.4, right? They look like they all go down momentarily, but you have to see beyond that and see, oh, okay, well, O2 ended up going up, CO ended up going up, and then it is CO2 that goes down ultimately. So reverse reaction has to be favored. Pressure has to have been decreased because reverse reaction leads to more number of moles of gas, hence increase in the pressure. Okay, 6.1.5. Let's take a look at that one. Write down the letter or formula of the gas that is represented by the letter Z. We already have the answer. 6.1.6. Give a reason for the answer to equation 3.1.5. Well, can I say we already have the answer? You know, can I say that we already have the answer? We already have the answer. Why am I saying that we already have the answer? We can see that when the pressure was decreased, the concentration of the reactants goes up, right? And we can see that concentration of X went up, which we know to be oxygen gas, and concentration of Z went up. It has to be carbon monoxide because that's the other reactants that we have. So write down the name of formula of letter Z, CO, carbon monoxide. You have the freedom of choice there. So that is 6.1.6. 6.1.7. What change in temperature is made at T is equals to 3? Choose between increase or decrease. T is equals to 3. So at T is equals to 3, O2 goes down. Carbon monoxide goes down. What does that mean? Forward reaction is favored, right? CO2 goes up, we can see. So forward reaction is favored. Let's go to our reaction and see whether our reaction is exothermic or endothermic. The forward reaction is exothermic, right? Forward reaction is favored. So it is the exothermic reaction that is favored, right? So which change in temperature favors exothermic reaction? Well, let's think. Endothermic absorbs heat, right? So if you increase temperature, endothermic is going to be favored so that it can absorb some of that heat, mitigating, right? And then if exothermic is favored, it means that temperature was reduced, and exothermic is favored so that it can release energy and the temperature can increase. So what change was made to the temperature at T3? If exothermic is favored, temperature was decreased, and if temperature is decreased, exothermic must be favored so that the temperature increases, because exothermic releases energy. That is 6.1.7, and we have answered 6.1.8. Use Lee-Chart gas principle to explain the answer to 6.1.7. And now the elephant in the room, 6.2. Carbon monoxide reacts with water, H2O, at T degrees Celsius. The reaction reaches equilibrium according to the balance equation. We have carbon monoxide plus H2O to give us CO2 plus H2O. And then we're given the initial number of moles of carbon monoxide, of H2O, of carbon dioxide, and of hydrogen gas. And then we're given the volume, which is 2 decimeter cube. How often do we find the volume of 2 decimeter cube? It's like it's an examiner's favorite, this volume of 2 decimeter cube. But anyway, stories. If the equilibrium constant Kc for this reaction at T degrees Celsius is 4, calculate the mass of carbon monoxide present in the flask at equilibrium. Okay, so let's go ahead and have our table, right? So yeah, obviously you can answer the question in the absence of a table, you know, but for the faint-hearted ones, me included in this case, let's use a table. Yeah, it's quite hectic when we don't have a table. Yeah, it's quite hectic when we don't have a table. Yeah, but it's doable. It's doable. I've been convinced that we can do it without a table, but I still prefer a table. Okay, so this is carbon monoxide, this is H2O, this is CO2, and then this is H2. The balancing coefficients, we have 1, 1, 1, 1, so we don't have to worry about that. And then here I'm going to put my initial number of moles. Here I'm going to put the change. Here I'm going to put the number of moles at equilibrium,
Here I'm going to put the concentration at equilibrium. So the number of carbon monoxide that I start with is 0.6. H2O 0.6. Carbon dioxide 0.1. H2 0.1. Our Kc is greater than 1, right? Our Kc is greater than 1. It is 4 actually, way greater than 1. So the forward reaction needs to have been favored in order for the Kc to be equals to 4. That is the first thing that we have to see, right? So what will be the change? With respect to the balancing coefficient, here we can have minus x, because the reactions, they're going down, they're getting used up. And then the products, we have plus x. So at equilibrium, we're going to have 0.6 minus x, 0.6 minus x, 0.1 plus x, 0.1 plus x. And then the concentration, we just divide by the volume. 0.6 minus x over 2, 0.6 minus x over 2, 0.1 plus x over 2, 0.1 plus x over 2. So Kc is equals to concentration of CO2 multiplied by the concentration of H2. Everything divided by concentration of carbon monoxide multiplied by the concentration of H2O. So what is the Kc? The Kc is 4. Concentration of CO2, that is 0.1 plus x over 2. And then H2, 0.1 plus x over 2. Everything divided by concentration of carbon monoxide, 0.6 minus x over 2, 0.6 minus x over 2. So let's solve for x. First thing first, 4 is equals to 0.1 plus x over 2 to the power 2, because they are multiplying each other, right? Divided by 0.6 minus x over 2, everything to the power 2. We can take square roots on both sides. I'm not going to write it down, but hopefully you can see that. You can see the consequence of taking square roots on both sides here. We will have 2 is equals to 0.1 plus x over 2, right? Everything divided by 0.6 minus x over 2. So 2 is equals to 0.1 plus x over 2 multiplied by 2 over 0.6 minus x. 2 and 2 cancels out. 2 is equals to 0.1 plus x over 0.6 minus x. So 1.2 minus 2x is equals to 0.1 plus x. So 1.2 minus 0.1, 1.1. Okay, I feel so stupid, but I don't want to make any mistakes. X plus 2x is equals to 3x. So x is equals to 1.1 divided by 3, which is 0.3667. What are we looking for again? The mass of carbon monoxide at equilibrium. So number of moles of carbon monoxide at equilibrium. Let's go to our table. Carbon monoxide at equilibrium, we have 0.6 minus x, is that right? So this is 0.6 minus 0.3667. Let me put that in my calculator. I get number of moles being equals to 0.2333 moles. So the number of the mass rather is equals to the number of moles multiplied by the molar mass. So we have 0.2333 molar mass of carbon monoxide. I think just 12 plus 16. So multiplied by 12 plus 16. This is 6.53. So 6.53 grams is equals to well, that's the mass of carbon monoxide at equilibrium. There we go. Iodine molecules dissociating to form iodine atoms in a reversible reaction. And then we are given the balanced equation, the Kc, and the corresponding temperature. And then 6.1 says write down the meaning
of the term reversible reaction. A reversible reaction is a reaction in which not only does the reactants form the products, but even the products form the reactants, right? And then 6.2 says, at equilibrium, the pressure of the system is increased by decreasing the volume of the container at constant temperature. And then how will each of the following be affected? Choose from increases, decreases, or remain the same. So 6.2, 6.2.1, the value of the equilibrium constant. We know fully well that the only thing that can change the value of the equilibrium constant is the temperature and nothing else. So we will easily say remains the same. And then 6.2.2 says the number of moles of iodine atoms, right? So we have I with the I2 basically, which is giving us 2I, right? So the number of moles of the products are greater than the number of moles of the reactants. And how do we know that? We can see using the balancing coefficients, right? Because we know fully well that the number of moles of I divided by number of moles of I2 will be equals to 2 divided by 1. So the number of moles of I is equals to 2 multiplied by the number of moles of I2. So we know that the number of moles of I are greater than the number of moles of I2. So when we increase the pressure, the system want to decrease that pressure, right? So it does that by favoring the reaction that leads to less number of moles. And the reaction that will lead to less number of moles is the reverse reaction, because it has the most number of moles, right? So 6.2.2 will say increases. So if it was vice versa and we were decreasing the pressure, then the forward reaction would be favored and we'd have a decrease in the number of moles of I2. And then 6.3 says explain the answer to question 6.2.2 by referring to Le Chatelier's principle. That is basically what I just did, right? What I just explained. The system wanna go back to a state of equilibrium. So if we increase something, the reaction that decreases that something will be favored. So we increase the pressure. So the reaction that leads to the less number of moles will be favored. That is the reverse and more number of I2 molecules. I hope that's clear. And then 6.4 says at 227 degrees Celsius, the Kc value for the reaction is 5.6 times 10 to the minus 12. Is the forward reaction endothermic or exothermic? So let's make sense of the Kc value first. So at 727, right, the Kc value is 3.76 times 10 minus 3. And then now we're told that at 227, the Kc value is 5.6 times 10 to the minus 12, much less than at 727. So we decrease the temperature and the Kc value went down, right? But what does the Kc value tells us? We know that when we want to calculate Kc, we say Kc is equals to basically the products, right? Divided by the reactants. That's what we are essentially saying. Although we'll square based on the balancing coefficients and all that, but then this is what we are essentially saying. So if we decrease temperature and the Kc value goes down, it means that now we have less products, right? We have less products. So the reverse reaction was favored by the decrease in temperature. Which reaction is favored by a decrease in temperature? That reaction is exothermic, right? So we're saying that the reverse reaction is exothermic. So that tells us consequently that the forward reaction is endothermic. And the question is asking us to explain whether it's endo or exo, right? The forward reaction. So we're gonna say for our answer endothermic, because we know fully well that the reverse reaction is exothermic because it was favored by a decrease in temperature. And then again, it says fully explain your answer, which is what I just did, right? So when you're explaining your answer, you can start by writing down these K values, explaining that Kc is basically products by reactants, and then you can see that when we decrease the temperature, there is less products, so the reverse reaction is favored. Which reaction is favored by decrease in temperature? That's exothermic. So the forward reaction is consequently endothermic. So let's do 6.5. 6.5 says a certain mass of iodine molecules, I2, is sold in a 12.3 decimeter cube flask at a temperature of 727 degrees Celsius, and we are given the corresponding Kc value. And then it goes on to say, when equilibrium is reached, the concentration of the iodine atoms is found to be 4.9 times 10 to the minus 3 mole per decimeter cube. And then we're supposed to calculate the initial mass of the iodine molecules. So before we go anywhere else, let's have our equation. So we have I2 giving us and getting back from 2I, right? So if we draw our table, we're gonna have the number of moles initial, the change in the number of moles, the number of moles in equilibrium, and the concentration, right? It says that for the concentration of the iodine atoms at equilibrium, we have 4.79 times 10 to the minus 3. So if we have this concentration here, we can then calculate this number of moles here, and then consequently get the change in the number of moles, because initially we had 0 here, right? So now we're gonna say the number of moles is equal to the concentration multiplied by the volume. What is the concentration? It's given as 4.79 times 10 to the minus 3, and then we're supposed to multiply it by a volume of 12.3. So if we do that, we're gonna get 0.058917, right? Is the number we get in here, 0.05817. So from 0 to 0.058917, it means we had a change of plus 0.05817. And then as a consequence, if we have a plus on the products, then we're supposed to have a minus on the reactants, right? Initially, we don't know the mass of the iodine molecules, so we cannot calculate the number of moles. But what we can do is just put N instead, right? And we're gonna solve it when we go forward. So here we're gonna have minus 0.05817 divided by 2. What is this 2 here for? This is because for I, we have a balancing coefficient of 2, and then for I2, we have a balancing coefficient of 1. So if you do that, so we're having 0.05817 divided by 2. So we're gonna have N minus 0.02985, right? And then the volume is 12.3. So here we're gonna have
n minus 0.02985 divided by 12.3. So now that we have the concentration at equilibrium, we can have Kc is equals to the concentration of I to the power of 2, because that's the products, right? Divided by the concentration of I2 to the power of 1, because that's the balancing coefficient of I2. But we are given the Kc as 4.79, actually as 3.6 by 10 to the minus 3, right? So we're going to have 3.76 by 10 to the minus 3 is equal to the concentration of I squared, which is 4.79 by 10 to the minus 3, divided by the concentration of I2 to the power of 1. That will be n minus 0.02985 divided by 12.3. So basically, for us to find the initial mass, we have to solve for n first, and then we're going to use n equals to the mass divided by the molar mass to calculate the mass, right? So if we do that, we're going to have I'll write it as n minus 0.02985 divided by 12.3 equals to 4.79 multiplied by 10 to the minus 3 squared. We have a square here. I forgot to write it. And then we're going to divide all of this by 3.76 multiplied by 10 to the minus 3. So we can actually break this n minus 0.02985 divided by 12.3, right? If we do that, we get n divided by 12.3 minus 0.02985 divided by 12.3, which is equals to this same expression. Nothing is changing, so I'm just gonna duplicate it instead of writing it again. So now we can take this term to the right hand side. So we're gonna get n divided by 12.3 is equals to, I'm gonna just duplicate the term instead of copying it again. So that term plus 0.02985 divided by 12.3. So now I'm going to multiply the left hand side and the right hand side by 12.3 so that I can get the value of n, right? So I'm multiplying this whole expression by 12.3. So n will be equals to, if you do the multiplication, you're going to get 0.105. And now we know fully well that n is equals to the mass divided by the molar mass. So what is the molar mass of I2, right? So we're gonna have 0.05 equals to the mass divided by 127 multiplied by 2. So the mass is 0.105 multiplied by 254, which is equals to 26.6 recurring grams.
Steam H2O reacts with hot carbon at 1000 degrees Celsius according to the following balanced equation. And there we have it. Initially, 36 grams of steam at a certain amount of carbon were placed in a 2 decimeter cube sealed container and allowed to react. At equilibrium, it was found that the amount of carbon changed by 0.225 moles. And then 6.1 says define the term dynamic equilibrium. Dynamic equilibrium is the same as chemical equilibrium. It's the stage in a chemical reaction when the rate of forward reaction equals the rate of reverse reaction.
Then 6.2 says calculate the equilibrium constant Kc for the reaction at 1000 degrees Celsius. So again, like we did on the other video, if you haven't watched it, subscribe to the channel and go check it out. So we're gonna start by writing the equation down. We have 2 H2O plus carbon in solid form, which is giving us 2 H2 plus CO2. So we're going to draw the table I did on the other video. Please, if you haven't watched it, please go watch it. So we have H2O, we have the carbon, we have the hydrogen, and we have the carbon dioxide. So what we're gonna have first is the initial number of moles, right? And then after we have the initial number of moles, we're gonna have the change in the number of moles. After the change in the number of moles, we're gonna have the number of moles in equilibrium. And then after that, we're gonna determine the concentration so that we can calculate the Kc. So it is said that initially we have a mass of 36 kg for H2O, right? And then the volume is equals to 2 decimeter cube. We know that the number of moles is given by the mass divided by the molar mass. The mass is 36, and then the molar mass for H2O is 18. So what is 36 divided by 18? That is 2 moles. So initially we have, let me change the color so that it's more visible. So initially we have 2 moles of H2O, and then we have 0 moles of H2, and then we have 0 moles of CO2. And then it is said that the amount of CO2 at equilibrium is 0.225, right? So that means that the change was also 0.225. And then for H2, we can determine that by using the balancing coefficients, right? So we're gonna see the number of moles of H2 divided by the number of moles of CO2 equals to the balancing coefficient of H2, which is 2, and then the balancing coefficient of CO2, which is 1. So basically, you multiply the number of moles of CO2 by 2, and that will give us 0.45. And then the same is true for H2O because the balancing coefficient is 2, right? Just like in H2. But then instead of adding for H2O, we're going to subtract, right? 0.45, because at that instant, the reaction that was being favored is the forward reaction, right? If it was vice versa, then we're going to add on H2O and subtract on CO2 and H2. So here we're going to have 0.45 because we're adding 0.45 and 0. And then for H2O, we're subtracting 0.45 from 2, and that will give us 1.55. And then the concentration at equilibrium, we know that the volume is 2, right? So we're just gonna divide 1.55 by 2, and that will give us 0.775. We divided 0.45 by 2, it gives us 0.225, and then 0.225 by 2. And that is going to give us 0.1125. And then the question would be, why am I not putting anything for the carbon, right? The carbon is a solid, and in chemical equilibrium, we are only interested in gaseous and aqueous solutions, right? We don't regard solids. So now we can write our equation. We can say that Kc is equals to the products, right, divided by the reactants. So what's the products? We know that we have H2, and then we're supposed to square it. Why are we squaring it? We're squaring it because it has a balancing coefficient of 2. And then we have CO2. And then the reactants, we're going to have H2O. And then we also square it because it has a balancing coefficient of 2. And then we don't regard the carbon because, like I've said, it's a solid. So we can go ahead and substitute those concentrations. So for H2, we have 0.225. So we're going to have 0.225 squared multiplied by the concentration of CO2. The concentration of CO2 is 0.1125. So we're going to have 0.1125. And then divided by the concentration of CO2, of H2O, which is 0.775. And then we square it. After we square it, we can then put it in a calculator, and we have determined our Kc. And that is 0.00942. And then we don't have any SI unit for Kc. So now we can move forward. We have 6.3.1. Then it says the graph shows how the rates of the forward and reverse reactions change with time. These are like the really interesting questions. And then 6.3.1 says, give a reason why the rate of forward reaction decreases between T0 and T1. The rate of the forward reaction is decreasing because the reactants are getting used up, right? So we have reactants are getting used up. And then 6.3.2 says, what change was made to the equilibrium mixture at T3? If both a forward reaction and reverse reaction are favored, they all go up at the same time, then a catalyst was added, right? So they added a catalyst. That is the only way both forward and reverse reaction can be favored at the same time. 6.3.3 says, is the forward reaction exothermic or endothermic? You can see that at T2, forward reaction shoots up, right? It goes up dramatically, and then it eventually starts going down because the reactants are starting to get used up. So at T2, the forward reaction is favored by the increase in temperature. And we know that an increase in temperature only favors endothermic reaction. So we're going to say 6.3.3, the forward reaction is endothermic. Why are we saying it's endothermic? We're saying it's endothermic because it was favored by an increase in temperature. And that's only true for an endothermic reaction. And then 6.3.4 says, refer to the chartelie principle to explain the answer to 6.3.3. That's what we just explained. The forward reaction is favored, and an increase in temperature only favors an endothermic reaction.
Consider the balance equation below for a hypothetical reaction that takes place in a sealed 2 decimeter cube container at 300 kelvins, that is. So our hypothetical reaction is happening between 2 atoms of P and 2 atoms of some element Q, which is giving us 2 atoms of PQ, right? I'm calling P not for us and just P because it's a hypothetical reaction. And then 6.1 says, define the term chemical equilibrium. Chemical equilibrium is a stage in a chemical reaction when the rate of forward reaction equals to the rate of the reverse reaction, right? And then 6.2 says, the amount of each substance present in the equilibrium mixture at 300 K is shown below in the table. And there we have the table there.
And then it goes on to say the temperature of the container is now increased to 350 kelvins. When a new equilibrium is established, it is found that 1.2 moles of P is present in the container. And then 6.2.1 says, is the heat of the reaction positive or negative? So at our initial equilibrium, the amount of the reactants, 2P and Q2, it's 0.8 and 0.8 moles, right? And then at 350 K, when the temperature is now increased, right, we have more products. We have more P from 0.8 to 1.2. That tells us that the reverse reaction was favored by the change. So that's why now we have more reactants. So if you increase the temperature, the reaction that will be favored is endothermic, and that's the reverse reaction. So the enthalpy, or the heat of the reaction of the forward reaction, is negative. So our answer for 6.2.1 will be negative, because the reverse reaction was favored by an increase of temperature. If the forward reaction was favored, then we're going to say the heat of our reaction is positive. So 6.2.2 says, use the Chartelie's principle to explain the answer to 6.2.1. I guess that's what I just did. I just, explained 6.2.2 as I was trying to justify 6.2.1. So 6.2.3 then says, calculate the equilibrium constant at 350 kelvins. We know that when we talk about the equilibrium constant, we use the concentration. So the first thing is for us to determine our volume, right? That will help us when we calculate the concentration. The volume is given in the equation as 2 decimeter cube, right? So that's something to note, because we're going to use that all the way going down. So now that we want to calculate the Kc, the equilibrium constant of the reaction, we have to form some sort of a table so that we can end up calculating the quantity at equilibrium. So what we're going to do, we're going to say 2 atoms of P plus 2 atoms of Q, they're giving us 2PQ. And then let me take out my ruler and just create that table. Yeah, so there we go. And then we have our initial number of moles, right? It is given on our table at 300K. For P, the initial is 0.8. And then for Q, it's also 0.8. And then for PQ is 3.2. And then we are told that at the new equilibrium, for P, we have 1.2. So here we'll have our change, and here we'll have our equilibrium concentration. So we are told that here at equilibrium for 2P, it's 1.2. So what's our change? If we find the change for P, then we can use the balancing coefficients to find the change for everything else. And then from there, we can find the concentration. We get our formula for Kc, we sub it in, and then we're basically done with the equation. So the change for P, to determine it, we'll subtract the moles at equilibrium by the initial moles. That will be 1.2 minus 0.8, which will give us 0.4, right? So if you wanna find the change, you subtract final from initial. Only makes sense. You do the same in physics. If you wanna find the change, you subtract the final by the initial. So now that we know the change for P, we can use the balancing coefficients to find the change for Q and the change for PQ. So we can see that for P and Q, for every is a 2:1 relationship. So let me just write that. So we have the number of moles of PQ, right? If we divide them by the number of moles of Q2, the balancing coefficients will be 2 divided by 1. So if you wanna find the change for Q, you divide the change for P by 2. So 0.4 divided by divided by 2, that will give us 0.2. And then for P and PQ, the balancing coefficients are the same. So in our equation here that we're establishing, we're just gonna, this was supposed to be P and not PQ. So here for PQ, we're just gonna have 2 divided by 2, which is just 1. So the change for P and the change for PQ is the same. It's also 0.4. So for Q2 at equilibrium, we'll get 0.8 plus 0.2, which will give us which is gonna give us 1, right? And then for PQ, we're gonna have 3.2 minus 0.4, which will give us 2.8. So why are we saying for Q? Why are we saying that for Q it's a plus and then for PQ it's a minus? Okay, this is what's happening. We have a reaction. If the products are increasing, the reactants are decreasing. So it is clear that the reactants are increasing, right? The reverse reaction is being favored. So for all the reactants, the change will add it to find the moles at equilibrium. But then from the products, because the reverse reaction is the one that's being favored, meaning that the products is getting depleted and is forming the reactants, we're going to have a minus instead. So that's why we're not saying plus 0.4, but we're saying minus 0.4, which is thus giving us 2.8. So when we get to this step, all we are left to do with is to find the concentration, and then we can substitute it in our equation. So we have already established that our volume is 2 decimeter cube. So for 2P, we're going to say 1.2 divided by 2, that will give us 0.6. And then for Q2, it will be 1 divided by 2, which will give us 0.5. And then for 2PQ, that will be 2.8 divided by 2, which will give us 1.4. So at this step, we can then say Kc equals to the products, the concentration of the products divided by the concentration of the reactants, right? And then this will be equals to the concentration of PQ squared. Where is the squared coming from? The squared is the balancing coefficient. When you put the concentration, you have to square it by the balancing coefficient. So for Q, which is in the denominator because it's the reactants, you can see that the balancing coefficient is 1. So we're just going to say to the power 1, or you don't have to write that because it's always assumed true. And then for P, we're going to have P to the power of 2 because the balancing coefficient is 2. So what's the concentration of PQ? That's 1.4. So we have 1.4 squared divided concentration for Q2 is 0.6 squared, and then the concentration for P is 0.5. And then after that, it's just a matter of putting it in the calculator, which I'm gonna do Yeah, real quick. So we have 1.4 squared divided by 0.6 squared multiplied by 0.5, which is equals to 10.89. And then we don't have any units for KC. Another thing to be aware of is that when we writing this formula for KC, we only regard reactants or products that are in gaseous or aqueous form. We don't consider solids. Okay, so that is that for that question. Let's move ahead. 6.2.4 says, how will the equilibrium constant in question 6.2.3 be affected when the volume of the container is decreased at constant temperature? Choose either increase or decrease or remain the same. Give a reason for your answer. It will remain the same. Let me just write that down. So it's gonna remain the same. It will remain the same because only temperature can change KC. That's always true. Only temperature can change KC, because if we increase or decrease the volume, then we have done that for both the reactants and both the products. So if it slows down the forward reaction, it's also going to slow down the reverse reaction equally. So KC at the end of the day is going to remain intact. The only thing that affects KC is the temperature. 6.3 says more Q2. Q2 is a reactant. So the reactant Q2 is now added to the reaction mixture at a constant temperature. How will each of the following be affected? Choose from increase, decrease, or remain the same. PQ. PQ is a product, so it's gonna increase, right? Because if we increase the reactants, then the forward reaction will be favored, so that we can establish our state of equilibrium. So the yield of PQ will increase. So basically what I'm saying is that if you increase the reactants, then the yield of the products will increase. If you increase the product, then the yield of the reactant of the reactants will increase, so the reverse reaction will be favored. And then 6.3.2 says the number of moles of P 2P and Q2, and then they're saying we increased Q2, right? So what will happen to P? The number of moles of P will go down, because the forward reaction will be favored if you increase the reactants, right? So 2P will be getting depleted at a higher rate. So for 6.3.2, that will be decreases.
The following equation represents a key reaction in the preparation of sulfuric acid. The process of the reaction is controlled in such a way that the temperature inside the container remains between 370 degrees Celsius and 550 degrees Celsious at all times. 6.1 says, what is represented by the double arrow in the equation? In chemistry, we know fully well that if we have a double arrow, it simply means that the reaction is reversible, right? So 6.1, you just write the reaction is reversible, and you get your 1 mark. And then 6.2 says, why is this reaction known as the contact process? It is known as the contact process because the reaction occurs in the presence of a catalyst, right? So the reaction is in contact with the catalyst, and therefore is known as the contact process. Now the question you might ask is, which catalyst do we need for this reaction? We need vanadium oxide, right? So the catalyst for our contact process is vanadium oxide, spelled vanadium oxide. But that's not what the question is asking us. The question just wants us to explain that it is known as the contact process because you are in contact with a catalyst, and you get your 1 mark. And then 6.3 says explain what the temperature is preferably not, and then 6.3.1 lower than 370 degrees. So they're telling us that for this reaction we need the temperature to be at least greater than 370 degrees. We need the reaction to be greater than 370 degrees because if the temperature is too low, right? If the temperature is too low, then the yield from the reaction will not be enough, right? Because you know that to increase the reaction rate, we need to increase the temperature, right? So that our yield can go up, right? So the temperature, if it's too low, the yield won't be enough. 6.3.2 says explain why the temperature is preferably not higher than 550 degrees Celsius. Let's look at our equation. Delta H is less than 0, right? So if you increase the temperature too much, then the reverse reaction will be favored. So you'll be basically converting your products back into reactants. And that's not what we want to achieve, right? So you must keep the temperature high enough, but you must not make it too high, because now the reverse reaction will be favored and we will get the reactants again. So here we're saying that a high temperature favors an endothermic reaction, right? A high temperature temp favors an endothermic reaction, right? Endothermic reaction. And then clearly the reverse reaction is endothermic, right? So our reverse reaction is endothermic. So if we increase the temperature, less products will be formed, right? So we're gonna have less products being formed. And then let's move to 6.4. 6.4 is saying for the process above, the following information is obtained from the analysis of the equilibrium mixture at 400 degrees Celsius. The volume of the container is 200 decimeter cube. The initial quantity of SO2 is 50 moles. And then the equilibrium quantity of SO3 is 22 mole. And then the Kc at 400 degrees Celsius is 7.328. Use the information above to calculate the initial mass of oxygen that was used for this reaction. So we're still going to follow the usual technique we use when we want to find Kc, right? But then the only difference here is that we're going to have a value for Kc. We're going to be solving for the oxygen, basically, right? For the number of moles of the oxygen. And then from the number of moles of the oxygen, we're going to be able to determine the mass, therefore. So we have 2 SO2 reacting with O2. And then this is giving us 2 SO3. We know that the reaction is reversible, so let's have that there. So here we need the initial number of moles, right? Here we need the change, and here we have the moles at equilibrium, right? And then here we have the concentration. So initially we had 50 moles of SO2, so there goes our 50,
And then for O2, we're not given, right? That's what we need to find so that we can consequently find the mass. And then for SO3, we're starting with 0, right? And then at equilibrium we have 22. So at equilibrium for SO2 we have 22, right? So the change here was plus 22. So now we need the change for O2, right? The balancing coefficient here is 2 and here it's 1, right? We usually don't write it, but we know there's a 1 here. So we basically divide in 22 by 2, which will give us 11, right? So if we were given 11 here and we're finding the number of moles of SO3, then we're gonna multiply by 2. For SO2, the balancing coefficients are the same, so we're gonna have 22 here, but we're converting the reactants to products, right? So here we're gonna have minus 11, here we're gonna have minus 22. So what is 50 minus 22? That is 28. And then what is x minus 11? X minus 11. And then now the concentration at equilibrium, right? So we divide in by a volume of 200 decimeter cube. So we have 28 divided by 200, x minus 11 divided by 200, and then we have 22 divided by 200. So now we can see that the Kc is equals to the concentration of the products divided by the concentration of the reactants. So if we go on with that, our product will only have SO3, right? So we're gonna have 22 divided by 200 to the power 2, right? The balancing coefficient divided by the reactants. So we have 28 divided by 200 for SO2, right? To the power 2 multiplied by x minus 11 divided by 200 to the power 1, the balancing coefficient. But we given the value of Kc, we know that it is 7.328. So now we have to solve for x. How are we gonna do that? What we can do here, we can say that x minus 11 divided by 200 is equals to 22 divided by 200 squared divided by 28 divided by 200 squared multiplied by 7.328, right? This step here might be confusing to some, but it's mathematically true, right? You can check it out and see if it works. So every time when you're solving a question like this in Kc, you can just take a term in the denominator and swap it with the term on the other side of the equation, right? It's true. And then from here, so let's multiply both sides by 200 so that we can get rid of this 200 here, right? So if we do that, we're gonna have x minus 11 is equals to 22 divided by 200 again squared divided by 28 divided by 200 squared multiplied by 7.328, and then we multiply in everything by 200, right? So now you can see that you just add 11 to both sides and you determine x. So if you add 11 to both sides, so let's take this entire expression, right? And then we say plus 11. So now we can erase this minus 11 here. We get x being equals to 27.849, right? So now we can use those number of moles to calculate the mass of O2 initially, right? So we know that the mass is equals to the number of moles multiplied by the molar mass. So that will be 27.849 multiplied by 16 multiplied by 2. Yes, so that will give you 891.167 grams. This is a bit lengthy. You can rewind the video so that you can get more clarity. So 6.5, last but not least, says the temperature for the process above is increased to 500 degrees Celsius. Consider the graph, and then there we have a graph. Which reaction, forward or reverse, is represented by the dotted lines? First of all, let's focus on the reverse reaction. We know that the reverse reaction is endothermic. So when we increase the temperature, the reverse reaction should be favored the most, right? More especially above 500 degrees Celsius. When we're close to reaching that 550 degrees Celsius, we're not supposed to reach for this reaction because the products will be too little, right? So when we increase the temperature, the reverse reaction will be favored. But the forward reaction will also be favored. But the reverse reaction will be favored more because it is endothermic. So hence, the dotted line and the other line, they all go up, right? But then you can see clearly that this solid line goes up way above the dotted lines, right? So it is more favored. Hence, the solid line is the reverse reaction. So the forward reaction is the dotted line. So the question is asking us to determine which line is the dotted line. The dotted line is the forward, right? Because we know that the reverse will be favored more than the forward if the reverse reaction is endothermic. There's a lot of weird things in this question. For instance, 6.2.1, we have 1 mark being awarded, and 6.2.2, that is still the case. But 6.3.3 is out of 8 marks. It doesn't make any sense. Let me show you why I'm saying that. So 6.1, we are asked to state Le Chatelier's principles. So what it essentially says is that if an equilibrium is disturbed, then the system will favor the reaction that opposes that disturbance, right, in attempt to reinstate a new equilibrium, right? So that is 6.1. Let's go ahead and do 6.2 and 6.2.1 so that you can see exactly what I'm talking about. So if we go through our question statement again here, you're gonna see that it says that 1 mole of pure hydrogen iodide gas is sold in a 1 decimeter cube container at 721 kelvins. Equilibrium is reached according to the following balance equation. So let's just copy down that balance equation real quick. So we have 2HI, and then we have H2 and I2. Right. So if we set up our table to calculate Kc, we're going to have something like the following. So let me just do that real quick. So here we're going to have the initial number of moles, right, on the first column, and then here we're going to have the change, and then here we're going to have the number of moles in equilibrium, and the last one we're going to have the concentration. So what we're given here is the initial number of moles of hydrogen iodide, right? It is said to be 1 mole, and then from there we're given the number of moles at equilibrium of I2. So the number of moles at equilibrium of I2, we have 0.11. Initially, we didn't have any H2 or I2, right? So we had 0 and 0 here. So it means that the change of I2 is plus 0.1, right? Not 0.1, but 0.11. Yeah, so we have 0.11 here. And then that is the change in the number of moles of I2. But then the change in the number of moles of I2 is the same as the change in the number of moles of H2, right? So we can put 0.11 here. We're saying that they're the same because we have the same balancing coefficient. But then when we come here, because now we have 2, we're gonna have 2 multiplied by 0.11, right? Which is 0.22. So we have 0.22 right there. So with that 0.22, we can then find the number of moles of HI at equilibrium, right? So it's gonna be 1 minus 0.22. That's how you do it. And then in the product signs, you just add. So 1 minus 0.22, I'm getting 0.78. So we have 0.78. Here we have 0.11. So 6.2.1, we're looking for the number of moles of H2 at equilibrium. We're looking for the number of moles of H2 at equilibrium. So here they are 0.11. So we have 0.11 moles. And then the number of moles of HI at equilibrium, here they are. We have them now, right? We have 0.78 moles. Right. And all this work just for 1 mark. That's what I was talking about when I say, yeah, I don't really understand the mark allocation in this question. Maybe there's a quick way of finding those number of moles at equilibrium. You can say that for H2, right? But then for HI, you really need to, take it a step further to find those number of moles at equilibrium. But anyway, stories. Let's move to the second question, to the third question, by the way. 6.3.1. The equilibrium constant Kc at 721 kelvins is 0.02. And then the temperature of the container is now increased to 850 K. The equilibrium constant Kc is now 0.09. So it has increased with an increase in temperature. What does that mean? Let's go ahead. So the first question is the forward reaction exothermic or endothermic? It is endothermic. It is endothermic. And why am I saying that? 6.3.2. We need to fully explain that. So what we know, right, just from the basics, is that an increase in temperature, let's not forget, let me just write this first. Kc is equal to the concentration of the products divided by the concentration of the reactants, right? So if Kc increase, it means that now we have more products. The forward reaction was favored. So the question is saying, is the forward reaction exothermic or is endothermic? The forward reaction is endothermic. That is because when the temperature was increased, we had more products, right? So it only makes sense that the forward reaction is endothermic. Because if you increase temperature, endothermic is favored. And as we can see that our Kc value has went up, we can clearly see that the forward reaction was indeed favored. Right. And then 6.3.38 marks. Right. Let's calculate the mass of HI present at the new equilibrium at 850 K. Right, so let's start with the initial number of moles. So the initial number of moles, we have 1, right, as we've already talked about. And then for H2 we have 0, for I2 we have 0, right? So we have that there. But then now we don't know the change anymore, because that change we had was for 721 kelvins. Now we're at 850. We don't know the change anymore, so we can put a variable in place of the change, right? We know that for the reactions you have to subtract. So let's say minus 2x, right? And then if this is minus 2x and we have a balancing coefficient of 2, then for H2 it should be plus x, because the balancing coefficient there is 1, and then plus x again, right? And then for HI at equilibrium, we're going to have 1 minus 2x. And then for H2, we're going to have 0 plus x, then 0 plus x. And now we move to the concentration. So the concentration, the volume is 1, right? And we know that concentration is equal to number of moles divided by volume. So the concentration will just be 1 minus 2x, x again. And then now we have our concentration at equilibrium in terms of x. Yeah, we can go ahead and set up our equation, our expression for Kc. It will be the concentration of H2 multiplied by the concentration of I2 divided by the concentration of Hi squared. We're squaring that because our coefficient here is 2. Right, so let's go ahead and substitute. In place of Kc, we're gonna have 0.09 being equals to the concentration of H2, that is x, concentration of I2, that is x again, and then everything divided by 1 minus 2x to the power 2. Right, so we're gonna have 0.09 being equals to x squared divided by 1 minus 2x, 2x squared. So what you can do here, you can cross multiply and complicate your life, or you can take square root on both sides. Let's take square roots on both sides so that I can show you what I'm talking about. So we can take the square root of 0.09, and then on the right hand side we can take the square root of this entire thing. So what is the square root of 0.09? That is 0.3. So we have 0.3 being equals to square root of x squared, that is x, and then in the denominator we're just gonna have 1 minus 2x. And just like that, we don't have a square anymore, because if we kept the square there, we would have to solve a quadratic equation, which is something I'm not really looking forward to. So if we cross multiply here, we're gonna get x being equals to 0.3, and then what is 0.3 multiplied by minus 2x? That is minus 0.6x. Right, so you can see that we can take this term to the left hand side. If we do that, we're gonna get 1.6x being equals to 0.3. So x is equals to 0.3 divided by 1.6. So what is 0.3 divided by 1.6? I'm getting 0.1875 moles. So the value of x is 0.1875 moles. But we're not looking for x. We're looking for the mass of Hi present at new equilibrium. The mass of Hi present at new equilibrium. So let's go ahead and find the number of moles of Hi at equilibrium. It's 1 minus 2x. So we can say that the number of moles will be equals to 1 minus 2x, but we now know what x is. It is 0.1875. So what is the number of moles? I'm getting 0.625, right? So we have 0.625. So we have the number of moles of Hi at equilibrium. Lastly, the mass will be equals to the number of moles multiplied by the molar mass. The number of moles is 0.625. I know that the molar mass of hydrogen is what? What's the molar mass of hydrogen again? I know that it is 1, right? How can we forget that? Now we just need the molar mass of I. That is 127, right? And then if I multiply those two, I'm getting 80 grams.